Good morning everyone, and thank you to ACDLabs for inviting me to speak today. I'll be talking today about the principles, advantages and potential pitfalls to avoid in retention modelling, and how this can facilitate the busy scientists in developing data they are confident in. To begin with, we will be discussing where models fit in with your work processes, and why you would benefit from performing retention modelling. Next, we will discuss the principles behind the models, which are based on empirical relationships. After this, we will look at practical tips and tricks to get the most out of your model, and then understand where we could cause problems in our models, which we need to avoid. Method development is one of the most critical activities performed in most labs. Often, it can be performed as a one factor at a time approach, which doesn't lend itself to smart working and streamlined processes. It is a drain of significant resources, including money, solvents, samples, and scientist time. A one factor at a time approach looks at one variable and establishes the best conditions with that one before moving on to the next parameter. The issue with that approach is that it does not establish intervariable relationships, and the most appropriate work spot can often be missed due to a lack of information. Instead of a one factor at a time approach, retention modelling allows us to create a design space with minimal experimental data based on chromatographic mathematical relationships. In this example, this design space would require 30 by 20 experiments to generate the plot, which would mean 600 experiments would need to be run. Solvent packages such as ACDLabs LC Simulator utilizes well-known chromatographic mathematical relationships to streamline method development to only require 4 input experiments, which is much more manageable. So how does retention modelling fit into your analytical workstream? To begin the whole process, we have the design of experiment stage, where we need to decide the aim of the separation. This includes any time restrictions based on the number of samples to be routinely run, or minimum resolution required. It also is a chance to probe the physical-chemical properties such as log P or D at a certain pH, and the pKa of the compounds and potential impurities. This can easily be determined using ACDLabs Perceptor. This information will feed into the decision-making for the method screening phase, which will allow us to determine appropriate organic modifiers, pH, column combinations. The screen is performed using one gradient time and temperature. The condition which possesses the most potential is then taken through to the method development stage, where the in silico modelling is performed to optimize the separation using LC Simulator. The final method is selected based on the best compromise. The model can then undergo robustness screening, where the software can predict retention for systematic errors in various operating parameters, including flow rate, mobile phase composition, and dwell volume. Then proceed to method validation based on whatever regulatory body you follow. It is important to also transfer the method between different users, different instruments, and different labs to ensure the methodology is entirely reliable. The method could then be released for routine use. There are several benefits to retention modelling. For this, I will highlight the main ones. To begin with, by performing the experiments required for modelling, we gain a lot of insight into the separation mechanisms for our compounds. The more information we have, the better our understanding of what occurs within our column with these analytes. From this, we also obtain highly optimized separations, which is due to us performing in a systematic manner, which looks at a range of chromatographic parameters. We significantly simplify our method development process. A one factor at a time approach, or worse, a scattergun approach, which randomly changes variables, does not allow us to establish intervariable relationships, and we could end up spending a lot of time chasing a separation, which we are never completely satisfied with. Following on from that, we obviously would save a lot of time, solvent and samples by constructing a model. There has been a big push recently to improve our sustainability and have greener methodologies, and a great way to implement that is to use in silico retention modelling. And lastly, we can select the most robust region to work in by looking at resolution maps between critical pairs. This allows us to determine how subtle changes in the method, such as slight deviations in flow rate, temperature, or dwell volume, can impact on the separation, and if there is too great a loss in method robustness, we may decide to not work in a particular design space. There are numerous models available within ACDLabs LC Simulator which look at the effect of pH, solvent ratios, or salt concentrations, or a combination of the above, as well as different modes, so reverse phase, normal phase, helical proteins. The end user selects the model most appropriate for the conditions they are investigating, which then changes the mathematical relationship. However, we will be looking at greater detail the most common parameters, which are percent organic and temperature. There is a plethora of literature available for you to look at, which perfectly describe the relationship between retention and percentage organic or temperature, which I encourage you to look into. However, I will briefly describe them. For small molecules in reverse phase chromatography, the percentage organic has a linear relationship to the log K of an analyte, where the retention changes as a function of organic in the mobile phase and a molecular descriptor. This is known as Snyder's linear strength solvent model. The slope is distinctive for each analyte. In a homologous series, the slope for each analyte is the same, thus changing the organic will not be a suitable parameter to change our selectivity. However, for compounds with differing physicochemical properties, the impact of percentage organic is different for each species, which then can allow for different selectivity, which is the foundation of retention modelling. By running only 2 experiments, a line can be drawn between each point and hopefully a percentage organic composition can be determined which would resolve all compounds. When we have biomolecules, however, the picture is a bit different. Biomolecules are particularly susceptible to small changes in organic composition, which is why they typically have long, shallow gradient methods. The conformation is highly influenced by organic content, thus a polynomial equation is required to describe the relationship. The same approach can be used for temperature using the Van 't Hoff equation, where 2 experimental points make a linear relationship, which can then highlight regions of separation. The differences observed are due to the enthalpy and entropy of each individual compound. We again need a different mathematical relationship which utilizes a polynomial equation for biomolecules due to the secondary structure conformational changes observed when we increase the temperature. Retention modelling software can have different levels for us to investigate based on the number of variables being investigated. Let's consider small molecule retention modelling. The first level is a one-dimensional model which considers a single parameter. This condition requires a minimum of 2 input runs and 1 validation run, which is halfway between the 2 extremes. The next level is a 2-dimensional model, which is by far the most common model, where 2 variables are changed. This results in 4 experimental points, which are used as inputs for your model, and 1 validation run in the very middle of the square. The final level is a 3-dimensional model, which changes 3 variables and is illustrated in this cube. There are 8 experimental data used to build the model at the corners of the design space, and 1 validation run. Moving forward in this presentation, we will be looking at the 2D model, as it is the most widely used approach. We want to obtain good data to create a good model, so we should follow these points. Before you begin any development, understand the aim of the separation and understand when enough is enough. We could spend precious time and resources trying to find the most perfect method, but instead we should define our criteria, then stop when that is met. We need to look at the physicochemical properties of the analytes of interest in order to find the most likely mobile phase and stationary phase candidates. Ensuring our pH is at least 2 pH units away from the pKa of our analytes will also improve the robustness of our separation by either fully protonating or deprotonating ionizable species. Of course, it's not always possible to have all analytes in one form, so it is making the best compromise in this situation. From the physicochemical properties of the analyte, we can make rational choices for our screening process and select options which will offer the best chance of separating the most compounds, whilst ensuring we don't cause any degradation to our compounds. It is important that we use a good column, and by this I mean a column we know will perform well. Ideally, this should be a new column, but this is not always possible, so in that circumstance, use a column with a known history which has not been exposed to ion pair and has a good efficiency. We should also ideally run all the experiments using the same batch of mobile phase and same column, in the same sequence, to ensure the integrity of our data. If this is not possible for some reason, then a run should be repeated between the different conditions to make sure that the data is reproducible, so it can be used as inputs for the model. Another good point is to run a validation data point, which has been previously described in this presentation. This center point can be used to cross-check the accuracy of the model. If the validation run is good, then we can proceed to spend time looking at potential conditions to resolve our compounds of interest. Next, ensure the instrument is performing well. If the machine is not pumping accurately or the flow rate isn't performing correctly, then we will not be able to create an accurate model. The model accuracy will improve with compounds eluting on the linear portion of the gradient. If peaks elute on the isocratic hold at the top of the gradient, the accuracies do reduce, so it is important to select appropriate conditions based on the column format to obtain an average K of 3 and 9. And finally, make sure that the column is fully equilibrated under each chromatographic condition before collecting data, and also ensure that you have enough column volumes in your post-run of your gradient to have reproducible results. This is typically around 10 column volumes. But please remember, your chromatographic models are only as good as your input runs. So if you don't take these initial precautions, you could end up with a rubbish model with rubbish predictions. The first thing you will need to build your model is the experimental data. So for a 2D model, it will be 4 experiments which need to be put into the model. We need to know the column dead volume and the instrument dwell volume. Poorly defining these values can lead to inaccurate predictions, which I will talk about in greater detail later. We also need to know the flow rate for the separation. Some optional information includes column dimensions, peak width, peak area, and peak tailing, which will help to improve the accuracy for the resolution predictions. So here we have a typical example of the results obtained once you input your chromatographic data. At the top we have our resolution map, which shows the gradient time on the x-axis and the temperature on the y-axis. The warmer red colours indicate greater resolution, whilst the blue regions are indicative of coelution. We obviously want to be working in the warmer regions. The great thing about LC Simulator is that wherever you click in your resolution map, you can see the corresponding chromatogram as illustrated at the bottom. It highlights the critical peaks in red in the chromatogram to easily show where the least resolution is obtained in the separation. There are several methods documented in the literature as to how to determine the dwell volume and extra column band broadening in the system. The dwell volume is measured between the points where the solvents meet and the head of the column. We need to know the dwell volume as the change in mobile phase composition will be different for each system, which means it plays a pivotal role in transferring a method between two LCs, such as between a UHPLC and a traditional HPLC. The use of a tracer with a chromophore in the mobile phase allows us to reasonably accurately determine the dwell. However, we can usually adjust the dwell volume value within the software to minimize differences in the model residuals. Once it has been measured once, it doesn't need to be remeasured unless the flow path has been drastically changed. The extra column band broadening is a measure of the contribution to peak dispersion that occurs outside of the column, which can cause the peak to spread. Its contribution is quite minimal on HPLC systems, but for UHPLC systems with efficient columns, the impact becomes more significant. By adjusting this value, it should describe the peak shape more accurately. The dead volume is the retention volume of an unretained compound. We can either approximate the dead volume or experimentally derive it. There are rough estimates for the column dead volume, which can be used to guide the end user. The first calculation is a pretty basic measurement of a cylinder, whilst the second calculation takes into account the porosity of the particle. This is important to differentiate between superficially porous particles and conventional totally porous particles. However, the better way to determine the dead volume is experimentally. But what is the best marker to use? Water and uracil are the most common T0 markers in reverse phase chromatography. However, we established that the value is highly influenced by the pH and the solvent composition. Here we have a plot of dead volume against acetonitrile content in the mobile phase at different pH values. The measured value does alter with different organic composition for both analytes. However, the biggest issue is at different pH values. Both markers gave greater deviation at pH 10.7, but more so with uracil. This is caused by the repulsion of uracil at pH 10.7 and the ionized silanols, whilst water is thought to penetrate the silica surface more deeply at high pH, so greater retained. Given that uracil is more affected by the change in pH, and water generally gives a clear negative peak for clear determination, I would recommend using water as the marker. Fortunately, the models can accurately predict retention with errors of plus or minus 20% in dead volume, where errors in the model would be less than 1% for both isocratic or gradient elution. But surely dwell volume doesn't cause that many issues. We were evaluating 8 compounds with a range of polarity. The validation experiments were in excellent agreement. However, when we used the model to predict the best separation, which started at 35% B, the predicted did not match the actual experiments. In fact, the percentage errors were in the range of 20 to 28%. Some %B versus log K experiments soon highlighted that the 3 most polar compounds were eluting isocratically with organic compositions greater than 25%, so the compounds were not focusing correctly at the head of the column. It was also established that although an experimentally derived dwell volume was used, the suggested value was greater in order to reduce the residuals. ACDLabs then introduced a dwell volume adjustment tool, which can change the dwell volume from the experimentally derived value to a suggested value, which can dramatically improve the accuracy of the model as shown chromatographically here. So errors can occur if the predicted initial %B is significantly higher than the input initial percentage B, and the analyte is relatively polar and doesn't stick to the head of the column before migrating down the column. To overcome this issue, use an iterative approach to determine the dwell volume to reduce the residual errors, or use the dwell volume adjustment tool for better guidance. So how accurate can we get our models? When we set up our experimental design, we set up 4 input runs, which are the blue circles in our schematic. We also include in our setup a validation run, which is the green circle in the schematic. This is a central point which is used to assess the validity of the model. A good fit between the experimental result and the predicted will give us confidence in the model. A poor correlation suggests that the model is not fit for purpose, so we shouldn't use it going forward. If we use this calculation highlighted, we can calculate the predicted error. For the retention time, anything less than 2% is often deemed good enough, although we can see from the results here that the percentage errors are very small, with 0.11 the largest deviation. The resolution value is a bit larger. However, it is important to remember to critically assess the data. If we interrogate the resolution between 4-chlorocinamic acid and ketoprofen, the error is 2%. However, the actual resolution was 3.6 and the prediction was 3.53, which is clearly within acceptable limits. One point of caution, however. If we use gradient inputs, we can very accurately predict gradient conditions. We can also accurately predict isocratic conditions from isocratic inputs. However, the problem arises if we try and use gradient inputs but develop an isocratic method from them. We can see that we observe greater errors associated with this for retention time and resolution. This is particularly problematic for early eluters. The resolution could potentially be caused by the broader peaks under isocratic conditions, whereas the peak width is generally the same under gradient conditions, provided they are of similar intensity. Biomolecules are a growing range of compounds which are showing interesting use in the pharmaceutical arena with targeted therapeutics, with 8 out of the top 10 pharmaceuticals based on sales being biomolecules. However, the models used to predict biomolecules used to have quite poor accuracies. But why is this? Let's consider paracetamol, a small molecule with a molecular weight of 151, which can be well modelled using conventional relationships. Then let's look at a protein, such as carbonic anhydrase, with a molecular weight of around 30,000 Dalton. It is quite clear to see there is a vast difference in complexity in their structures. As I previously described, the mathematical relationships are more complex than for typical small molecules, which the Van 't Hoff or linear solvent strip models were based upon. If we look at this Van 't Hoff plot, we can visualize that as the temperature increases, the conformation changes for the protein, and then we have this banana-shaped curve where the protein conformation fully changes. Therefore, for a 2D model, we would require more experimental data points to be able to describe the design space. Instead of the 4 input runs for small molecules, we would have a 3x3 experimental run with 1 validation run to properly describe a biomolecule. To address these structural issues, ACDLabs added a model which utilizes a second-order equation to better describe the relationship between percentage organic or temperature with larger biomolecules such as peptides and proteins. We can see in the below example a resolution map for a peptide and tryptic digest impurities with a method development based on the maximum resolution in the red zone. The predicted separation on the right-hand side is in red, and we can see from the black trace that the main peak and the impurities are well modelled. It's important to remember to create a method where the compounds of interest elute away from the solvent front to avoid matrix effects. There are, however, various sources of error which can cause issues for our models. The first pitfall for potential modelling comes from our data. If we have poor quality data, we will inevitably have a poor quality model. Rubbish in, rubbish out. We need to put the time in to obtain good quality data by hopefully using some of the hints and tips previously described. Our next issue is peak assignment. Peak attribution is quite possibly the biggest Achilles heel of retention modelling. The task is made more manageable when we use complementary techniques such as diode array detection, mass spec, and peak area. There are softwares which can assist with peak attribution. However, they all struggle with isobaric species or compounds with similar chromophore, but progress is being made to try and sort this. Peak shape modelling is not generally as accurate as retention time. However, it is pretty reasonable for peaks of equal intensity. This helps to make resolution predictions more accurate. It is, however, very difficult for the software to predict the peak shape for overloaded asymmetrical peaks, often seen for API peaks. The next error is often associated with typos or transcription errors. This can occur when the data processing is not connected to the modelling software. However, if data is processed with ACDLabs Spectra's processor, it can be transferred quite seamlessly into LC Simulator, minimizing this risk. As is often the way with most software, there are a vast number of functions which are not fully utilized, which could help the end user. So I would encourage you to speak with any software provider to try and get the most out of your software to help with your day-to-day workflow. And finally, time is often spent to generate these models. However, we often don't share all the information with people downstream, so it would be advantageous for modelling information to be shared. For example, we could redevelop methods based on the model if necessary. So, in conclusion, we require good data to be used as inputs for us to achieve a good model. With poor data, we will only generate a poor model. We need to spend time establishing what the aim of the separation is in order to direct the development process and make the most out of our model. We can gain a significant amount of information from retention modelling, which can facilitate the product and time analytical life cycle, from method development, through method robustness studies, through to method transfer and routine use. This information is gathered from very few input runs, which allows us to work in a more sustainable and logical manner. We saw earlier that the equivalent number of individual experiments to generate a 2D model would be approximately 600 experiments, but with in silico modelling, we can reduce that down to just 4 manageable experiments. However, we need to spend time interrogating our data thoroughly to ensure we track our peaks correctly, and misidentification will affect the accuracy of our models. And finally, we can obtain accurate models for both small conventional molecules as well as larger biomolecules, provided we select the most appropriate mathematical relationship. So with that, I'd like to thank ACDLabs again for the opportunity to speak today and for providing Shimadzu UK with the Method Development Suite software. And thank you for listening. If there are any questions, I'd be happy to answer those now.